So let's see some examples of how to do work and energy problems. So we're first going to start with this problem asking us how much work is done by a boy pulling his sister 30 meters in a wagon as shown in figure 7.36. This is in the OpenStax college physics textbook, and assume that no friction acts on the wagon. So I've kind of recreated this picture for us below, and we can see that this boy is pulling on this wagon at a 30-degree angle from the horizontal, and they're going to move a total distance of 30 meters. So to figure out how much work I'm doing, I first need to know the definition of work. I know that work is defined as being equal to a force times the change in position times the distance that we move times the cosine of the angle between that force and that distance. So I can look at this problem, and I've actually been given almost everything that I need. Okay. In the picture, they show us that the force that we're pulling at is equal to 50 newtons. So we can plug that in. So we have our force. We know the distance that we're going is 30 meters, so we have our distance, and the angle between the two is given as 30 degrees. So we can simply plug and chug into this to find the work. The work is equal to the force, which we're given in the picture is 50 newtons, times the distance that we travel, which is 30 meters, times the cosine of 30 degrees. So if you plug all of this into your calculator, you will find a work that's equal to 1.3 times 10 to the third joules. And that's the basic idea behind solving a work problem. You kind of plug in your various values for your forces, your distances, and your thetas. So now we want to see how to solve kind of energy problems, how to use the energy equations that we know. So in this particular problem, we want to know how fast a 3,000 kilogram elephant has to move to have the same kinetic energy as a 65 kilogram sprinter that's running at 10 meters per second. And then we want to know how larger energy is needed for the movement of larger animals relates to metabolic rates. So how do we go about solving this numerical part? So we should start this like we start all physics problems by basically writing down everything that we're given. We are first given the mass of this elephant. We'll call it mass E. That's equal to 3,000 kilograms. And we want to know how fast it has to move to have the same kinetic energy as a 65 kilogram sprinter. So we have the mass of the sprinter that is 65 kilograms. And we know that the velocity of this sprinter is moving at 10 meters per second. And I want to know about its kinetic energy. In particular, I want to know how much velocity the elephant needs. So I need to know what VE is. I need to find this so that the kinetic energy of the elephant is going to be equal to the kinetic energy of the sprinter. The equation for kinetic energy is equal to 1/2 whatever your mass is. So this would be on the right-hand side, mass of the sprinter, times the velocity of the sprinter squared. And I would have the same equation for the elephant on the left-hand side. 1/2 the mass of the elephant times the velocity of the elephant squared. Now I can do algebra, and I can solve this equation for VE, the velocity of the elephant, which is what I'm looking for. So when I do that algebra, I can see that my 1/2s will both divide out and cancel out. I can divide both sides by ME. And then I can take the MEs will cancel out on the left-hand side, and then I can take the square root of both sides, and that will get rid of my squared on the left-hand side. So I get a final equation for VE. VE is going to be equal to the square root of mass of the sprinter times velocity of the sprinter squared, all divided by the mass of the elephant. And now I can just plug and chug my numbers in. My mass of my sprinter in this equation is going to be 65 kilograms times the velocity of the sprinter, which was given as 10 meters per second. And we divide by the mass of the elephant, which is 3,000 kilograms. And the velocity of the elephant is going to have is equal to 1.47 meters per second. So I take the square root of the multiplication of all these numbers, and I get my final answer of 1.47 meters per second. So that's part A. Now, part B, discuss how the larger energies needed for the movement of larger animals would relate to metabolic rates. To discuss how these larger energies needed for movement of larger animals relates to metabolic rates, we need to know what a metabolic rate is. So metabolic rate is the energy used by some kind of animal to do something per unit time. And what I can tell from this problem is that my elephant, to have the same energy as a 65 kilogram sprinter running at 10 meters per second, they need a very small velocity of about 1.4 meters per second. So if I want to get up to that same velocity as that sprinter, if my elephant wants to get that fast, they need to use a whole lot more energy. So what this tells you is that the metabolic rate for your larger animal to get your velocity from 1.4 meters per second up to v equals 10 meters per second, your elephant is going to have to expend a whole lot more energy than the runner is going to have to expend. So they're going to have a higher metabolic rate for this elephant.